Okay, so we'll start. So what we see last time is the Cauchy criterion for convergence, right? So we have proved that right. So we have proved that Cauchy if and only if convergence, right? So if the sequence is Cauchy, then we say it is convergent. At the same time, if it is convergent, then we can prove that it is Cauchy. So this is how we do this. So now what we are going to do is we are going to use this to verify the convergence of a sequence, right? So instead of showing the convergence of a sequence, if we show that the sequence is Cauchy, then we can say that it is convergent. And vice versa, if we want to show the sequence does not converge, you can always show that the sequence is not Cauchy, right? So both ways it will work. So I'm going to give you two examples. One of them I will do and the other one I will leave as an exercise. In both cases, we are going to show that the sequence is not convergent. Right? So in both cases, we are going to show that these sequences are not Cauchy or not convergent. So one of them we are going to show, right? So we shall show this by using that the fact that they are not Cauchy, right? So right, so they ask you to show that the sequence is not convergent, right? So they want to show you not convergent. So if you want to show not convergent, here I am going to use this result. Convergent gives Cauchy and Cauchy gives convergent. So not convergence gives not Cauchy and not Cauchy gives not convergent. So I will show, right? Right, so we shall show these sequences are not Cauchy. Right? So I will do the first one. You can try the other ones, right? So if you want to show Cauchy, right, you have to first assume that it is Cauchy, and you get a contradiction, right? So here I will write. Right, so we assume that this one is Cauchy. Right, so if you assume that this is Cauchy, then you know the definition, right? I'm going to choose epsilon is equal to half, right? So then there exists some n1 belongs to natural number such that xn minus xm is less than half for all m comma n greater than n1. That is a definition we write for Cauchy sequence. Right. right? So you have this. So basically this is what you have, right? So you look at this, this is 1 plus 1 upon 2 plus all the way up to 1 upon n, right? Minus 1 plus 1 upon 2 all the way up to 1 upon m, right? It's less than half. That is what you have, right? So now you have to choose whether this has more components or this has more components, right? M and N are greater than N1, but you don't know which one is greater. But if you choose any one as greater, it does not make any difference, right? So if you say M is bigger than N, that is also fine. And if you say N is bigger than M, then that is also fine. So I'm going to use So I'm going to use N greater than M. WLG is without loss of generality, right? So that means the meaning of this is this. Right? So without just loss of generality, that is the meaning of WLG. Right? So WLG. So that means if you choose the other way around, M greater than N, that is also give you the same kind of results, right? So that does not make any difference. Choosing M or N larger does not give any difference in the solution or in the way you handle the problem. So that is why you can choose any way you like. So without loss of generality, we take N greater than M. So obviously, you know, if N greater than M, this has more terms, right? So somewhere here in the middle, you know, there will be 1 upon M plus 1 upon M plus 1, and things will be here in the middle, right? So 1 upon M plus 1, and so up to things like that will be here. So when you subtract, what you get is right. So you will have 1 upon M plus 1 plus 1 upon M plus 2 all the way up to plus 1 upon N is less than half. That is what you have. So here this is true for all M comma N greater than N1. At the same time, you assume that N is greater than M also. Right, so you choose this to be greater than M. Right, so now what we have to do is we are having M and N, two numbers. So we will try to make it as one unknown number, that is M. Right, so because M is the smallest, so we will try to write N in terms of N, right? So we can choose N, right? N can be any number bigger than M. At the same time, it should be bigger than N1, right? So obviously M is also greater than N1, so N1 does not matters here, but you can always choose N as any number bigger than M. Because N is bigger than M, you can choose N as 2M, right? So what you have is this. right? So you choose n as 2m. So obviously m plus 1 is smaller than, m plus 1 is larger than, smaller than 2m. So 1 upon 2m is smaller than n plus 1, right? So 1 upon 2m is smaller than 1 upon n plus 1. 1 upon 2m is smaller than 1 upon n plus 2, right? And so all the way up to, and then 1 upon 2m is equal to 1 upon n, because you choose n as 2m. All the others are strictly smaller, right? So eventually this inequality holds, right? But this one you say is less than half, right? Because of your assumption, Cauchy assumption, you know that 1 upon n plus 1, 1 upon n plus 2 up to 1 upon n is less than half. So you have summation of 1 upon 2m is less than half, right? And you notice that this is m times, right? So there are m plus 1, n plus 2 up to 2m times. So there are m times, right? In this case, m times 1 upon 2m is strictly less than half. Right? So this is a contradiction. Right? So then this is true for all n, m greater than n1. This is also true for all m greater than n1. You know that? So now you can see that to cancel m and m, you get 1 upon 2 is strictly less than 1 upon 2. And that is not possible. Right? So it has to be equal. And there is no equal sign. It is strict inequality. So that is a contradiction. And because this is a contradiction, our assumption is wrong. So this cannot be Cauchy. Okay, so if that is not Cauchy, then it is not convergent. So this is how you can use the Cauchy criterion to verify the convergence of a sequence, right? So you can either verify whether the sequence is convergent by looking at whether it is Cauchy or not. At the same time, you can always verify whether the sequence is Cauchy by looking at whether it is convergent or not. Right? So both ways you can use the theorem. It is called Cauchy criterion. And second example, I leave it as an exercise for you. So you can try at your home, same idea. You try to use Cauchy, or you try to assume that it is Cauchy and get a convergent, right? So clearly, you know, there is a minus 1 to the power n term, right? So you obviously know if you have minus 1 to the power n, you have to choose one of your n as in even number and the other one as odd number, right? So if you choose m as odd and n as even, or you can choose n as odd and m as even, then you can fix that, right? So you will try to get a contradiction, something like this. So that's how you do the problem. Right, so that's an exercise. Now what we are going to do is we are going to talk about some consequences which arise from the boundedness of the sequence. And so this is something we learn, right? Right, so we say that convergent implies bounded is something we show earlier, right? Any convergent sequence is bounded. But we have seen also that boundedness does not imply convergent, right? We see an example, the very famous example, minus 1 to the power n. That sequence is bounded, but not convergent, right? So that is the famous example for boundedness does not imply convergence. So clearly, you know, if you have a bounded sequence, you cannot say whether the sequence is convergent or not, right? So sometimes some sequence may converge, but not necessarily all the sequence. So, but because it is bounded, right? Because the sequence is bounded by the property, supremum property or the completeness property you studied in the first chapter, right? That says if the set of real numbers is bounded above, then it will have a supremum. Right? And if the set is bounded below, then non-empty set, if it is bounded below, then it will have an infimum. So you know that as long as the sequence is bounded, you can always find a supremum for the set and infimum for the set. So you can make subsets of sequences, right? So this is how you are going to do. Okay, so now suppose that you have a sequence xn bounded, right? So you know the set of elements contained by xn is bounded, right? So that is clear. So now what I am going to do is I am going to create a sequence of sets. So first I am going to take, okay, let me take x1, right? So not x1, right? For some, so without x1, right? So x2, x3, and so on. Maybe I can make another set x3, x4, and then I can go all the way up to xn, xn plus 1, all the way up to this. So I can make several subsets of the set of all elements of the sequences, right? So this is any element whose index is greater or equal to 1, right? So you can see the definition, right? So this is xi such that I greater than 1. So this is a set of xi such that I greater than 2. This is a set of xi such that I greater than n. So I am making subsets of the elements of the sequences. But because xn is bounded, I know this set is bounded, this set is bounded, this set is bounded. And all these sets are bounded. So what I can do, if it is a bounded sequence, then what I can do is I can take the supremum and infimum of the sets. And so let me name this as set A1, set A2, up to set AN. And I can continue further also. So I am getting sets, subsets of the set of elements of sequences. So A1 is a bounded set. So it will have a supremum and it will have an infimum. A2 is a bounded set. So it will have a supremum and it will have an infimum. So what I am going to do is I am going to create a new sequence. Right? Now, what I am going to do is I am going to create a new sequence. My capital M1 is supremum of A1. My capital M2 is my supremum of A2. And all the way up to Mn is the supremum of An. And I can continue doing this. So in this way, I am creating a sequence Mn which are supremums of the certain subsets. Similarly, I can do small m. One is infimum of A1. So up to I can create a sequence Mn, right, which are infimum of the sets. So obviously they are also real number sequences. So I have created two sequences from a set of bounded sequences. One is the sequence of supremum and the other one is the sequence of infimum. So then I have a sequence here, I have a sequence here. And then I can see that, right, if the set is bounded, right? Obviously, this sequence is also bounded below, right? So because the set is bounded, this sequence is bounded below, right? So this will have a minimum value among these supremums. You can find the minimum value, or it is bounded below, right? So capital Mn is bounded below. At the same time, sequence of infimums are bounded above. And because the sequence is bounded, it is bounded above and bounded below. So if it is bounded below, then it will have a limit, right? So because if the sequence is monotonically increasing or decreasing and bounded below, then it will goes to a limit and this will goes to a limit. So in both cases, you can try to find limits of sequences, right? One of them is basically the infimum of the supremums. Take all the sequence of supremums and then that converges to a bounded below. So because it is bounded below, you can make it convert to some limit. And this is bounded above, you can make it convert to some limit. But not necessarily the limits are same. And this goes to a different limit, this goes to a different limit. So those limits are slightly different from our regular limit, right? Because we say limit xn goes to n goes to infinity is equal to L, then that is the only limit. But here from one set you are getting two different limits, right? One is the limit of the supremums and the other one is the limit of the infimum. So we have to name them. So we will name them as upper limit and lower limit, right? So that is what I'm going to define now, the upper limit and lower limit based on these constructions. So now let me write down it properly. Okay, so let me explain you again. Right. First thing is, so the concept is about upper limits and lower limits. So the first thing is, you know that not all bounded sequences have a limit. So we will try to see what kind of limits they will have, right, if they have something. So first take a bounded sequence xn, and then you define set of elements in the sequences, right, over certain fixed index, right? So the index is higher than k, then you name it the set of all elements with the index greater than k as ak. So then clearly, because xn is a bounded sequence, ak is also a bounded set because all the elements are bounded in that set. And also because you choose k as natural numbers, when you increases k, right, when k goes from k to k plus 1, the number of components in the set is getting one less. because if you take k is equal to 1, you have elements from 2, 3, 4, 5, 6, so and up all the way. And then if you take k is equal to 2, then you will have 3, 4, 5, 6. Right? So then obviously that has one element less. Right? So if you go to k5, then you will have 4 elements less, and so on. Right? So in that case, you can see that if k increases, the set become smaller. Right? When k increases, the set becomes smaller. That means the set is contained in the previous set. And because the set is bounded, AK is bounded, you can confirm that there exists a supremum and there exists an infimum. And it is obviously not empty, so you can confirm the existence of supremum and infimum. And because supremum and infimum exists, and at the same time, the set is getting small, 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 so supremum will obviously get smaller, because when you take a supremum of a small set, it becomes lesser than the supremum of a larger set. We studied that in first chapter. Similarly, when you take infimum of small set, it will get bigger, right? So that is also we studied in the first section. So supremum is a decreasing sequence in this case, and infimum is an increasing sequence in this case. But anyways, because the set is bounded, elements are bounded, so supremum and infimum are obviously bounded. So decreasing sequence bounded below, so it will have a limit. Increasing sequence bounded above will have a limit. So what we do is we will take the limit of the supremums. Right? We call it upper limit. So we put a bar above the limit. Right? And then we take limits of the infimums. So that we call lower limit. And we put a bar below that. Right? So that is how we define upper limit and lower limit. Right? So limit of the supremums is called upper limit, and limit of the infimum is called lower limit. Right? So this is how we define upper limit and lower limit. Now what I am going to do is I am going to do an example where we compute the upper limit and lower limit of a sequence. Right? So as a remark, let me just okay, so let me just remind you one little remark before going into the problem, right? Right, so the upper limit and lower limit are not necessarily equal, right? Right, so these two limits are not necessarily equal, right? So you cannot expect always the limit of both are same, right? So there are special cases where the limits are same, and that we will talk later on, right? So first we will try to find the limit, right? So let me say example. So let me name a set xn, a sequence xn, which is 1 upon n. Right? So you know, you can say AK is set of all xn such that n greater or equal to k. So that is obviously 1 upon k, 1 upon k plus 1, and so on. This is how your set looks like, because n greater or equal to k. So 1 upon k, 1 upon k plus 1, right? 1 upon k plus 2, and so on. right? So you increase when you take AK, it becomes 1 upon k plus 1, and so on, right? So this is how your set looks like, right? So if this is the set, then you can see that the supremum of AK, right? The supremum of AK is obviously 1 upon K, right? Because the upper bound is 1 upon K, right? So that is 1 upon K. At the same time, you can find right, you can find infimum of AK is 0. That is something we did in the first chapter. Right, finding supremum and infimum. Right. So this is because of the fact that, right, you know the set of all elements AK, right? AK is this set. Right? So right, so for every element AN, right, so I can say small a. That's what for every element small a in the set AK, you know that it is obviously strictly greater than 0, right? Because this number goes all the way to 0, right? But not equal to 0, so strictly greater than 0. At the same time, all the components in this set are less or equal to K. So by using that and using the completeness property, you can verify supremum is this and infimum is this. So now what you do is you take K goes to infinity, supremum of AK. Right? So that is limit of K goes to infinity 1 upon K, and that is 0. Right? So this is upper limit of xn, right? And goes to infinity. And similarly, if you take the supremum or infimum and limit, right? Limit of K goes to infinity, infimum of AK, right? So that is clearly limit of K goes to infinity 0, that is 0. So here limit of n goes to infinity xn, lower limit. So you have found both the limits, upper limit and lower limit of the sequence, right? So upper supremum is 1 upon K and limit of the supremum is 0 and infimum is 0, limit of 0 is 0. So in this case, you can notice that both upper limit and lower limit are same, right? So here both upper limit and lower limit are same. So that is why we say that the limit of this sequence is 0, right? So we already know that this limit of this sequence is 0. That is, we studied very early, right? So in the case when the limit exists, then you can kind of see that the upper limit and the lower limit are same. Right? If they are not equal, then you see that the limit does not exist. So in this we will talk a little bit more about this upper limit and lower limit and in the tomorrow's class, and after that we will move on to the next chapter, which is about seals. We have to talk a little bit more about upper limit and lower limit. Hopefully we will finish that in the next class, and if we cannot, we will take one more class and then we will go into the series, right? So that we will talk about that in the tomorrow 1 o'clock class. Right? So we'll stop here and then continue tomorrow.